In this video, we'll be discussing half-lives, which are related to our previous discussions on the integrated rate laws. So, when we were previously talking about integrated rate laws, the purpose of them was to determine the concentration of a particular component at a given time. The half-life is a very specific time. The half-life is the time interval that it takes for the initial concentration to fall to 1/2 of its initial value. Right? So the concentration becomes 1/2 what it was before. The graph over here is looking at a first order process. For a first order process, the time that it takes for half of the concentration to go away or to have reacted is a specific length of time. For first order processes, this is actually independent of concentration. And so each half-life is the same length of time. We will see that for a 0th order and a 2nd order, this is not the case. The half-lives change with concentration. When we are trying to determine an equation for the half-life occurs when our time is equal to t1/2. So we'll take in our integrated rate laws, wherever we see t, we're going to change that to t1/2. And our concentration of A at time t, we're going to set this to 1/2 our initial concentration. So essentially what we will do is we will take the integrated rate laws and replace t with t1/2 and A at time t with 1/2 A0. We can then solve for our concentrations and our time and come up with expressions that will relate time to how long it takes for the concentration to be cut in half, which is our half-life equations. So if we're trying to find an expression to determine the half-life, we can use the fact that the half-life itself is defined as the length of time it takes for half of the reactant to disappear. So what we will do is we'll set, wherever we see A at time t, we're going to set that to 1/2 A0, right? Because we're interested in the length of time that it takes for the concentration to be half of what it started out as. And its starting concentration is A0, so we're looking for the concentration to be 1/2 of that value. We're going to replace our t with t1/2, so we will solve for t1/2 in our integrated rate law. So what we're going to do is take a look at our various examples. So we'll take our A at time t, set that to 1/2 A0, and we'll change our t to be t1/2. So if we do that for our 0th order reaction, that would give us 1/2 A0 minus A0 is equal to minus K times t1/2. Okay, we can combine the left-hand side, right? 1/2 A0 minus A0 is negative 1/2 A0. We have a negative on both sides, so if we multiply it by -1, that will cancel out our negatives, right? Which will give us an expression of K t1/2 is equal to 1/2 A0. Now we're interested in having an equation with the t1/2 all by itself, so we will divide both sides by our K, our rate constant. Right? On the left-hand side, this will cause the K to cancel out, and we'll be left with an expression for our half-life. So we get t1/2 is equal to our concentration of A at time 0 divided by 2. This is the same thing as our 1/2 A0, 2 times K. Okay, so this is our expression for figuring out our half-life for a 0 order or a 0th order reaction. And we'll make that t a lowercase t because it is time. We can do the same thing for our first order process. So this would give us the natural log of 1/2 our concentration of A0 minus natural log of A0 is equal to minus kt 1/2. Now there are a couple rules that we have with logarithms that are going to help us out. The two rules that we're going to be using are essentially the natural log of a minus the natural log of b is equal to the natural log of the ratio of a over b. The other one that we'll be using is the natural log of a over b is equal to the negative of the natural log of the reversed fraction, b over a. So if we flip a fraction, a over b, inside a logarithm, we get the negative of the logarithm, of the logarithm of the inverse, right? So the natural log of a over b is equal to the negative of the natural log of b over a. We will use these two rules for natural logs in our derivation for the half-life equation for a first order process. So we can see that we can use our first one right here. We are subtracting two natural logs. So we can combine them together to give us the natural log of the quantity 1/2 a naught divided by a naught is equal to minus kt 1/2. Okay, we have our a naughts are directly on top of each other in a fraction, and so they will cancel each other out. So this would give us the natural log of 1/2. Now we can note that we have a negative sign here on our k value, and so if we flip our ratio, right, we can actually get rid of that negative sign. So I'm going to flip the ratio. That gives me the natural log of 2 is equal to the negative of negative kt 1/2, which would just be kt 1/2. I can divide both sides by k, and that will get rid of k on the right-hand side. And now I have an expression for the half-life. So for a first order process, t 1/2 is equal to the natural log of 2 over my rate constant, little k. The interesting thing about this is in our half-life expression, there is no concentrations. What that tells us is that for a particular species, the half-life is a constant value. As long as we're not changing temperature, which would affect our k value, the half-life is the half-life. It does not change. So when we have an initial concentration, if we cut it in half, the next half-life is the exact same value. Okay, let's finish this off for the second order process. So we're going to replace our a times t with 1/2 a naught and our t with t 1/2. So we get 1 over 1/2 a naught minus 1 over a naught is equal to kt 1/2. Now we have 1 over 1/2 starting out. That's the same thing as 2 over a naught. So this is equal to 2 over concentration of a naught minus 1 over the concentration of a naught. So that would be giving us 1 over concentration of a naught. Okay, that's equal to kt 1/2. We can divide both sides by k. Divide both sides by k. That's a parenthesis. Okay, and we get an expression of, well, our k's cancel out. And we get an expression of our t 1/2 is equal to 1 over our k value times our initial concentration. What this tells us is that the higher our concentration is, the smaller the half-life will be. So as we work with larger and larger concentrations for a second order process, the half-life will get smaller and smaller. the bigger the A naught value is. But what it also means is as the process continues in time, each sequential half-life will take longer. Whereas in the case of a zero-order process, because the concentration is up top, the less you have, the faster it goes to get the next half-life. A real-world example of where half-life gets used is determining how old things are. Because all radioactive decay follows a first-order decomposition reaction, and as we just learned, all first-order processes, the half-life is a constant value. It is independent of our concentrations. So we can use this to figure out how long ago the components started to decay. Now, carbon-14 itself is continuously produced in our atmosphere via neutron capture. So when high-energy cosmic rays from the sun interact with the upper atmosphere, they release neutrons. Those neutrons can be captured by nitrogen-14, nitrogen-14 being the most prominent isotope of nitrogen, and nitrogen N2 makes up 78% of our atmosphere. So the neutrons that are emitted by the upper atmosphere when they interact with cosmic rays, they get absorbed by carbon-14, which then undergoes proton emission, right? So you got your nitrogen-14, captures a neutron, quickly undergoes proton emission, and you get carbon-14. Now, carbon-14 is a radioactive isotope. It will break down over time. So because all radioactive decay occurs via first-order kinetics, carbon-14 breaks down via beta decay, so it gives off a beta particle, and reforms nitrogen-14. Now, we can tell how old things are from this process by particularly looking at plant-based material. So plants are continuously taking in carbon dioxide and incorporating that carbon into their structure via carbohydrates and cellular structures. When an organism dies, it stops pulling in carbon-14. Now, because the carbon-14 is decaying over time, the carbon-14 concentration is continuously dropping. If we compare the carbon-14 concentration that an object has compared to the amount of carbon-14 that it should have had when the plant materials that it's made out of died, we can determine how long ago the plant that it was made out of died. And typically when an object like an archaeological object is made, the plant material is not all that much older than the object. So by measuring the ratio of carbon-12 to carbon-14, we can determine how old something is. Let's look at an example of using carbon-14 dating to figure out how old something is. Now, about 1,000 years ago, Vikings actually sailed across the Atlantic Ocean and made it to North America. One of these Vikings was Thorfinn Karlsefni, who is believed to have started a colony in North America roughly 1,000 years ago. Let's say that a family in Maine unearthed what appears to be a wooden ship hull, and they want to know, was this Viking ship from 1,000 years ago? Well, what we can do is look at the ratio of carbon-14 to carbon-12 of the wood, and we find that the ratio from this theoretical sample, let's say that the concentration is 1.43 parts per trillion. What that means is that out of every trillion carbon-12s, 1.43 of them is carbon-14. Now, the natural abundance of carbon-14 to carbon-12 in a living organism, one that is still pulling in fresh carbon-14 from the atmosphere, is 1.5 parts per trillion. Now, the half-life of carbon-14 is 5,730 years. we want to know how old our wooden sample is. Well, what we can do is use our equation for half-life of a first-order process. We know it's first order because this is radioactive decay, and all radioactive decay is a first-order process. So we can use our integrated rate law to determine how old the object is. We can, using our integrated rate law for a first-order process, the natural log of the concentration of A at time t minus the natural log of our concentration initially is equal to minus kT. Now, before we start plugging in numbers, we can actually simplify this up using our rules from our natural logs, right? The natural log of A minus ln of B is equal to the natural log of A over B, and the natural log of A over B is equal to the negative of the natural log of B over A. We can rearrange our equation to be the natural log of our concentration of A at time t over the natural log of A naught is equal to minus kT. That's using our first rule. We can now use our second rule to get rid of the negative sign on the right-hand side. So the natural log of our concentration A naught over concentration of A at time t is equal to kT. If we're interested ultimately in the time, we could divide both sides by k, and we get an equation for our time. Right? So the length of time that something has been undergoing radioactive decay is equal to our equation on the left-hand side. The problem we have is we don't know what our rate constant is. But if we take a look at our half-life equation, we can actually find the rate constant if we know the half-life. So the half-life equation for a first-order process is T1/2. The half-life is equal to the natural log of 2 divided by our k value. We know the half-life, we know natural log of 2, so if we rearrange this equation to solve for k, we can actually figure out what our k value is. So we would move our k to the left and move our T1/2 to the right. This gives us k is equal, little k, is equal to the natural log of 2 divided by the half-life. So this would be natural log of 2 divided by 5,730 years. Right? This will give us a value for our rate constant that has units of per year. So if we plug that in, our k would be equal to 1.20968 times 10 to the negative 4 per year, or year to the negative 1. This essentially means that our unit for year is on the bottom. We can plug all that into our expression that we have here, right, which gives us the natural log of A naught, which is our concentration initially, which would be 1.50 ppt, divided by our concentration that we now find is 1.43 parts per trillion. Okay, we take that and then we're going to divide that by our k value, which is 1.20968 times 10 to the negative 4 years to the negative 1, right? Now, on our ratio here, the units cancel each other out, and so we get natural log of 1.50 divided by 1.43. that whole quantity divided by our K value would be equal to 395.00726 years. Now, obviously, this is way too many significant figures. So going back and trying to figure out how many significant figures we should have, the number of significant figures on our K value, the natural log of 2 is a whole number, and so it doesn't come into play. Our half-life has 3 significant figures, and so our K value will have 3 significant figures. The value up top, our ratio, when we're all done, is going to have, before we do the natural log, it will have 2 decimal places. You take the natural log of that will give you 2 significant figures. So our value would cut here. We have 2 sig figs on top, 3 on the bottom, and so our end answer would be about 400, with the sig fig being at the tens place. So if we do 4.0 times 10 to the second years, which is 400 years, with the sig fig being right there. So essentially what this is saying is that the wood is 400 years old, so it could not be from Thorfinn Karlsefni.